Hi everyone. So in this video, we will talk about the stepwise regression. So stepwise regression is a way to find the, not to find, but to search in the optimum subset of different x variables in the presence of multicollinearity. Okay. So remember, we said that some x variables, x1 and x2, although we call them as independent variables, they can be dependent on each other, which means, well, they just screen their own effect to the dependent variable y, which just reduces the quality of the linear regression. In order to circumvent this problem, we have some methods. One of them is called the stepwise regression. So in the stepwise regression, we just each variable enters or exits from the model one by one. So it's actually a modified version of the forward selection method, which is in fact, well, it's joint use of forward and backward selection. We will talk about both of them in details. Okay. So in forward selection method, well, there are two important questions. So what we do is we just add each variable one by one. So at each step, we just check, well, which variable has the greatest impact, okay? So in order to answer the question, we just check the R square. Then the next question is, well, okay, this one is the greatest, but is this impact, is this impact significant, okay? So adding this one, of course, this has the greatest impact, but whether this impact is significant or not. What we do is we just check the p-value of the t-test. Remember, so we have tests at each line, or we have f-test in ANOVA, right? We just check the p-value of this t-test. If it is significant, we said that, okay, I can add this value, okay? So for example, let's start with step one. So choose the x variable that gives the highest largest R square value among the simple linear regression models, beta 0 plus beta k x k, okay? So for our particular baby weight example, just check beta 0 plus beta 1 x1, beta 0 plus beta 2 x2, beta 0 plus beta 3 x3, and beta x4 x4, beta 4 x4. So if assume that, well, this one has the greatest R square. Okay, this is the first step. And the next step, check whether this is significant or not. If it is not significant, if p-value is too large, then just stop the algorithm, because this has the greatest R square, but even if this is the largest one, it is not significant. So what we do is we just stop. Okay, we just stop the algorithm. In step two, what we do is, well, beta 1 x1 is already in the model, right? What we do is, well, we just now check the other variables. We just add the other variables to the model and check which of them has the largest R square, okay? So we just add the variable x2 to the model, then x3 and x4. I have three different models, and check which one has the greatest R square, okay? So let's assume that this one has the greatest R square, okay? Again, then check the p-value. P-value, how to check p-value? We just check the p-value of the hypothesis whether beta 2 is equal to 0 or not, okay? We will see in detail in the example, but so if we cannot reject the hypothesis, again, we just stop here, because this has the greatest R square. Even if this is greatest, it's not significant, so we just stop here. If it is significant, we add the variable to the model and proceed to the next step, okay? So in the next step, what we do is we just choose the variable that, when inserted in the model, has the greatest R square. So in the next step, what we do is we just check, we just add beta 3, or we just add x3 and then x4 to the model and just compare two models and see which one has the greatest R square, okay? So assume that if it is x3 and if x3 is not significant, then we stop. Otherwise, we just continue with the next step, right? Okay. So what is the backward elimination method? So this was the forward. This the previous one was the forward selection, and the other one is the backward elimination. Okay, so in the backward elimination method, what we do is we just start with all variables, okay, all of the x variables in the model, and then we just find the variable which has the smallest contribution to the R square. Okay, just find the one which has the smallest R square. Say that it is x1. So if the contribution of x1 is not significant, just remove. Okay. Then in step 2, okay, assume that, well, it was x1. Now in step 2, you have a linear regression with the remaining variables, which is x2, x3, and x4. Okay. So what you do is, again, you just get a regression with the remaining 3 variables, check which one has the smallest impact, smallest contribution to R square, and then check whether it is significant or not. If it is not significant, and then remove it as well. Okay. So stepwise regression is in fact an improved version of the forward selection, or it's a mixture of forward and backward algorithms. Okay. So, well, so in stepwise regression, what we do is at each step, when we just add a variable, we just check whether is there any other variables that can be removed from the model. Okay, so what we do is we just add one variable. Okay, so we just take a step, then take another step. Okay, then we just check whether so for example, we just add x1 to this model, then we just add x2 to this model, then we just check whether we can we remove x1 from the model, then we just include x2, right? So what we do is we just apply forward and backwards in a joint match. Okay, so what this is because it's possible, let's read this, that a variable entering the regression equation at an early stage may become insignificant after some other variables enters at a later stage. Okay, this is why, this is because this may happen due to the collinearity between these variables. So at each step, what we do is we just make a partial f-test, or we may just make equivalent t-test, which is easier. Okay? For all variables in the model to see whether they are still significant or not. And if they are not significant, we just drop them from the model. So this procedure stops when no additional variable can be inserted or deleted in the model. Okay, so we will just make we will just apply this stepwise regression procedure on the on our infant data. Okay. So remember, so we have the y variable, the dependent variable, which is the length of an infant to the variables, the length of an infant, and we just search whether y is dependent on the age in terms of days, length at birth in terms of centimeters, weight at birth in terms of kilograms, and chest size at birth in terms of centimeters. Okay. So we want to see whether y depends on these variables or not. Right? So what we do is, first we feed the 4 simple regression models for each xi, okay? So we just fit whether y is equal to, we just fit y to x1, then y to x2, then x3 and x4, and just check the highest SSR or highest R square. Okay? So, well, so this is the Excel file that I use to just make the regression. So this is the data, this is the Y data, this is X1, this is X3. So sorry for having another order here, but that's not a big deal. This is X3, X4, and X2. So at first, what we do is we just make a regression only on X1, okay? So see, this is beta 0 and beta 1 only. The others are not included. This is a regression for y and x2 only, y and x3, y and x4. Okay. So what we do is we just check the SSR. Okay, the SSR, right? So just look at the SSR of the first one where we have x1. Okay. So SSR is 288 here. SSR here is 215. SSR is 186, and here SSR is 100. Okay, so which one is the largest one? This one is the largest one. Okay, so since r square is equal to, I don't know whether I can write here or not, but let me just write it here. Since r square is equal to SSR divided by SST, and remember SST is constant, right? Why? Because I have yi minus y bar squared. So y bar is the same. It doesn't depend on the regression line. Yi, they are the observed values. It's the same. So SST is the same. So having the largest SSR is equal to having the largest having the largest R square. Okay. So just look at here. So R square here in this model is 90%. R square here is 67%. Okay, let me just make this smaller and make this as percent, right? And let me just make this as percent. This is 90%. This is X3, this is 58%. And this is, again, this is 31%. Okay, so which one is the largest one? This one is the largest one. So this is the first part of step one. Find the largest variable that has the largest contribution. So X1 has the largest contribution. The next step is, well, check whether this contribution is significant or not. Okay? So whether this is significant or not. So just look at here. Remember the first line. Okay, I have the same thing here, right? Okay, I have the same thing here. So look at this one. This is the result of this regression line, which has y0. Let me see. Okay, so this is the output for y is equal to beta 0 plus beta 1 x1, right? So beta 0 turns out to be 19, and beta 1 turns out to be 0.52. And this is the t-stats that t observed, okay? And this is the p-value for this hypothesis. What is the hypothesis here? Whether beta 1 is equal to 0 or not, okay? So by just looking at this p-value, can we reject this hypothesis? Well, yes, I can reject the hypothesis and say that, well, beta 1 is not equal to 0. And just remember, so beta 1 equal to 0, this is our null hypothesis. This one refers to y is equal to beta 0 plus some epsilon, right? And h1, beta 1 is not equal to 0. It means that y, sorry for this. So that's equal to y is that refers to beta 0 plus beta 1 x1 plus epsilon, right? Okay, so I just reject the hypothesis and say that, well, this is my model. And this model has an R square of 90%, okay? So step one is okay. We just add x1 and we just proceed to step two, okay? So in step two, what we do is we just add, okay, we just add x2, x3, and x4 to the existing model. So what we will do is we will just check these models. Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2, right? And the second model is beta 0 plus beta 1 x1, beta 3 x3, right? And then see this, beta 0 plus beta 1 x1 plus beta 4 x4, right? Just look at the R square or the SSR of these three models and pick the one which has the largest one, okay? And then check whether this contribution is significant or not, okay? So how can we find this? So just look at this one, okay? We say that we can find, okay, let's look at this at first. Okay, so what is R beta 2, beta 1, beta 2? This is in fact the SSR, the regression sum of squares, okay, when you have beta 1 and beta 2 in the model. And what is this? Okay, this is the representation of SSR when you only have beta 1 in the model. Okay, just go back, it was 288. Let's look at this one. Okay, 288.1, 288.1. So this is SSR beta 1, right? And this is SSR beta 1 and beta 2. This is a different representation. Okay, so this is the regression. Okay, regression when you have beta 1 and beta 3 in the model. So this is again SSR when you have beta 1 and beta 3 in the model. So the SSR when you have beta 3 and beta, so let's look at this one. Okay, this one refers to the SSR of this one. This one refers to this one, and the other one. Okay, let me just put that here. Okay, this refers to this one. So this is what? This is beta 1 and beta 2. That's 312.02, and the other one 317.46, and this one 301.96. So which one is greater? This one is greater, right? We can also check this in my Excel file, right? So this is x1 and x2. Just look at here, 312. This is the SSR of x1 and x2, right? Just look at here, 312, x1 and x2. And the other one, x1 and x3, 317, right? 317.46, 317.46. And the last one, x1 and x4, 301.96, 301.96, right? So which one is larger? This one is larger. So our candidate point is x3. Now, okay, now the question is whether adding, whether the contribution of x3 is significant. By the way, so I can define this thing, okay? R beta 2 given beta 1, that's equal to 23.87. So what does this mean? This means, well, the contribution of beta 2 given that beta 1 is already in the model. Okay, so how can we find this? This is equal to, in fact, this is equal to S of, let's say this is R beta 1 and beta 2. The SSR when we have beta 1 and beta 2 in the model minus if there is only beta 1 in the model. So what is this? This is 312.02 minus 288.1. Okay, if you just subtract this, then the resulting thing is, so 302, so this is 288, right? That's 28, but 88, right? So this is 23.87. So this is the contribution of beta 2 when there is already beta 1 in the model. Similarly, you can find this as R of beta 1, beta 3 minus R of beta 1, right? And this is R of beta 1 and beta 4 minus R of beta 1, right? So which one is largest contribution? It's this one, okay? So you can find it from here or here. They are the same. So both of them has the same result. They just show which one has the greatest impact. Now the question is whether this impact is significant or not. How do we check this? Okay, so this is my model. Okay, so this is my candidate model, beta 1 x1, beta 3 x3. Okay, so now the question is whether adding beta 3 to the existing model is significant or not. How? I just checked this. H0. So look at this table. This table is for this regression. So what I do is beta, not 0, but beta 3 is equal to 0 versus beta 3 is not equal to 0, okay? So when you just look at the p-value, it turns out that what you reject the hypothesis and say that, well, beta 3 is not equal to 0. So again, for the sake of completeness, let me just write here, it says beta 1 x1, right? And the second, the alternative hypothesis states that you have this model, okay? So when you reject the null hypothesis, it means that your data refers to, your data has, let's say, evidence in favor of this model, okay? Hence, our new model is this one, right? Okay. So the next step is, remember now I'm in stepwise regression. I just added the second variable. I will just check whether can we remove x1 or not, okay? So in fact, my question is, well, let me just write here, H0 beta 1, okay, beta 1 is equal to 0 versus, right, beta 1 is not equal to 0. So I'm just checking this. Y is equal to beta 0 plus now beta 3x3, right, versus beta 0 plus beta 1x1 plus beta 3x3, okay, this one. So if you cannot reject this hypothesis, it means that, well, use this model. If you reject the hypothesis, it means that, well, adding x1 to this model is still significant, okay? Or removing x1 makes a significant loss in your model. So when you just look at the p-value, it says that, well, just reject the hypothesis, okay? Hence, well, still I have this model. Now the next step. Okay, now what I will do is, let me just write it here. Well, I have beta 1x1, beta 3x3. So I have now two models to check, whether beta 0 plus beta 1x1 plus beta 3x3, okay, plus beta 2x2 versus, let's say, y, beta 0, beta 1x1 plus beta 3x3, right, plus now beta 4x4. So which one to choose, okay, which one to choose? How can we make this? We can just check the largest R square or find this one. Again, let me just write how to find this one. This is R of beta 1, beta 2, beta 3, okay, minus R of beta 1, beta 3. So what does this say? This just gives you the contribution of beta 2 when you have beta 1 and beta 3 existing in your model. And similarly, this one, so I can just write this. This is R of what? Beta 1, beta 3, beta 4, minus R of what? Beta 1 and beta 3, right? So this one just shows you the contribution of beta 4 when beta 1 and beta 3 exists in the models. Okay. So again, let's look at the x1, x3, okay, x1, x2, x3, x1, x3, x4. We'll just look which one has the largest SSR. Okay, so this is x1, x2, x3. This is x1, x3, x4. It turns out that this has the largest what? This has the largest SSR, or this has the largest R square, right? And so I can find the additional effect of what? Additional effect of x2 by comparing this one with what? With this one, right? So I can just write, for example, this is equal to this one minus the previous model was x1 and x3, okay, this one. So the resulting, so this is what this is. Let me just write here. This is R of what? R of beta 2, right? The R of beta 2. Similarly, I can find the R of beta 4, R of beta 4, that's equal to 317.64 minus my origin of the previous model was this one, okay? This. So this is equal to 0.19. 0.19 and 0.79, just look at here, 0.19 and 0.79, okay? Now my candidate point is this, okay? My candidate point is this, right? So, okay. Now the question is this contribution significant or not? Okay, let me check this. What they do is we just look at the again the result in terms of the hypothesis test. Okay, so this is the following is the output for this model, right? Beta 1x1, beta 3x3, and beta 2x2. So at this line, I'm just trying to check whether adding this thing is significant or not. The p-value is high, which means that you cannot reject the hypothesis. So what is the hypothesis here? So let me just write it like this. Beta 2 is equal to 0, which refers to y is equal to beta 0 plus beta 1x1 plus beta 3x3 versus beta is not equal to 0, right? Which is equal to beta 0 plus beta 1x1, right? And plus beta 3x3 plus beta 2x2. So this says that, well, you cannot reject the hypothesis, and, well, this hypothesis is selected, which means your model is still beta 1x1 and beta 3x3. Okay? You cannot add x2 because it doesn't have a significant contribution to the model, right? So the algorithm just stops here because I cannot add anything. In the previous step, I see that I cannot remove anything from this model, so we just stop here, right? So the best model that we have put is this, right? The best model that we have found is this. Okay. So y hat is equal to 20, almost 20 plus 0.4138 x1, 2.0253 x3. Okay, so with r squared, so this is very high, 98.8%, and s squared is 0.63. Okay, so both of them are pretty high. Well, different procedures may choose different models, right? So just look at this another model. So remember, in the previous stepwise regression or forward regression, in fact, if we just used forward regression, we would have find the same model as it, right? It was beta 1x1 plus beta 3x. So the R square is 991 and S square is 0.51. And these are slightly better than the model found by the stepwise and or let's say forward regression. Okay. So which was this one, right? Well, the stepwise procedure did not observe this combination of x2 and x3. Okay. But if you just have used the backward elimination, which is start from the full model and then eliminate each variable one by one, then we would have end up with this model, right? X2 and X3. So different models may end up with different procedures may end up with different models. This is because, well, the stepwise procedure or the forward procedure are myopic policies. Okay, if you choose, they are myopic policies in terms of they do not look two or step forwards ahead. What do they do is they are just greedy search. What they do is at each step they just add the most let's say the variable which has the greatest impact. Okay.